Hello everyone, my name is Shenli Tang, a PhD student from University of Tokyo Kavli IPMU. The title of my today's talk is the spectroscopic study of dual quasars with HC SSP. The aim of this program is to study the co-evolution of supermassive black hole and their host galaxies in the merger phase using dual quasars. To get a sample set of dual quasars, we start with matching the SDSS DR14 quasar catalog with the HSC DR2 catalog to get high-quality optical images with eye-bound resolution around 0.6 arcsecond of the SDSS quasars. This cross-matching sample set includes 34,000 quasars. We then model the images with PSFs plus Thirsic profiles, and the candidates are selected as those being modeled by 2 or more PSFs. This reduces the number to 452. After doing visual inspections, this left us with 401 candidates as I'm showing in this figure. Here the gray dots are the SDSS DR14 quasars, and the colored dots are those we selected out as candidates. And the filled dots are what we have observed in this program, and the green star marks are the dual quasars we have already confirmed. And the pink star marks are projected quasar pairs, that is a quasar pair at different redshift. With the spectroscopic data in hand, we are able to measure the black hole masses for type 1 pairs using Viro method. The result is shown in the left bottom figure here. So we compare the black hole masses of our binary quasars with those single quasars in the SDSS-DR14 quasar catalog. We find that they have comparable black hole masses. We see our binary quasars are distributed quite uniform in this large catalog. Also, we find the mass ratio of low redshift binary quasars are all within 5 to 1, with only one exception here, which is a quasar pair at redshift 3, and their black hole mass ratio is 7.72. We suggest that this is because at earlier universe, the environment is gas-richer. Therefore, even for the minor mergers, it is able to trigger on enough gas inflow onto the central supermassive black hole and activate it. On the other hand, from the image decomposition which we used to select out our candidates, another thing we can benefit from that method is to estimate the Thirsic model magnitudes of the host galaxies, and we set the criterion to be within redshift 1. We then use Seagull to do SED fitting to get the stellar masses of these systems. And we find most of our binary quasars are located in the green valley, and they are relatively massive, as you can see here. So we suggest that this could indicate an enhanced star forming activity in these systems. Now, taking this together, we are able to study the black hole host correlation. But first, I would like to show you some results from the simulation where we can trace all the process of the merger. So here, the left panel shows the black hole mass versus stellar mass, and the second panel shows the evolution of black hole mass versus redshift, and the third panel shows the evolution of stellar mass versus redshift. The thick black line here is the local relationship taken from Ding et al. 2020, and the same color refer to the same pair, and the star marks refer to the primary sources, and the dot marks refer to the secondary sources. Now I'm showing the first stage when both sources are labeled as AGN in the simulation. Actually, we can already see that they are following a linear-like relationship, but just with a little bit over massive black holes in these systems. Now to the second stage, their host galaxies merge first, so we see the data points reduced from 10 to 5 data points here, and we see an increase in the stellar mass, however, by not so much. Also, the increase of the black hole mass is also moderate. Now to the third stage, the black holes merge. Now we see a boost in the black hole mass here, and the growth of the stellar mass is still moderate. The final stage is a coalescence stage. Now, taking all these together, we would like to compare that to our observations. Now, I'm plotting our observation results in a similar fashion, but now our binary quasars are plotted as these dot marks, and we sum them up to those star marks to mimicking their possible final stages. And the gray dots are the single quasars taken from SDSS for comparison. We find that first, the single quasars do not apparently follow the local correlation due to intrinsic biases that need to be applied. But when we look at a black hole mass versus stellar mass correlation, we find similar things both in the simulation and in our observation. So please focus on the dots and the first stage I just mentioned. So we see that this correlation is already exist before the merger. Therefore, they are not established by mergers as suggested by some studies. What merger do is rather like something like bring the systems of this relationship due to a higher black hole fusion efficiency relative to star formation and feedback effect. As I mentioned in the second panel, there's a boost in the black hole mass, while in the third panel, the growth of the host galaxy is not significant. Okay, so this is the end of my talk. Thank you for your attention.